Hey guys, this is Professor Janacek, and I want to talk about circular functions versus hyperbolic functions. Let's begin with circular functions. The unit circle has an equation of x squared plus y squared is equal to 1. If we graph that, of course, we get a circle that's centered at the origin with radius 1. And the x and y describe each and every point on that circle. Okay, now what we can do is we can add, let me go ahead and draw a little right triangle in there. Let's call that, the angle in there, let's call that t. And using this t is how we will define our circular functions. Turns out, looking at that t, we know that the sine of t is equal to y, and the cosine of t is equal to x. And that's how our circular functions are defined. That's just 2 of them. We have a set of 6 circular functions, but I'll let you look at those. That's what trigonometry is all about. So those are the 2 basic circular functions. Just real quick before we look at the hyperbolic functions, I want to remind you that the equation of a circle, now this was the equation of a unit circle, but the equation of a general circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. And if you recall, an ellipse is actually very similar. The equation of ellipse is x minus h quantity squared over a squared plus y minus k quantity squared over b squared is equal to 1. All right, now what about the hyperbolic functions? Well, the unit hyperbola is very similar to the unit circle. The equation for the unit hyperbola is x squared minus y squared is equal to 1. And you have something similar. You have the unit hyperbola is a hyperbola. And the vertex is there at positive 1 and negative 1. Oh, there's a negative 1 on that one. Shouldn't be negative. Let's fix that. Okay. There we go. So the vertex on the hyperbola, the vertices are positive 1 and negative 1. We could do a similar thing. Let's go ahead and, of course, the x and y in the equation describe any point. And if we measure the angle from the x-axis up to that point, we'll call that t. And then we can define our hyperbolic functions on that. So the hyperbolic sine of t is equal to y, and hyperbolic cosine of t is equal to x. And again, there are 6 there are 6 hyperbolic functions. I have them described down here. So I give you the definition for just the hyperbolic sine and hyperbolic cosine. Hyperbolic sine is e to the x minus e to the negative x over 2. Hyperbolic cosine is defined to be e to the x plus e to the negative x over 2. So they're very, very similar. And then I give you not definitions but properties for the remaining hyperbolic trig functions. We've got hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. And they are connected to the sine and hyperbolic sine and hyperbolic cosine functions in a similar way that the trigonometric functions are connected. And I do also want to just remind you that the equation of a hyperbola looks like x minus h quantity squared over a squared minus y minus k quantity squared over b squared is equal to 1. So notice it's very similar to the equation of an ellipse, but we have subtraction there in between. Or it could be written as y minus k quantity squared over a squared minus x minus h quantity squared over b squared is equal to 1, depending on its orientation. And remember, subtraction is not commutative, so you have to distinguish which one comes first, the x or the y. Well, there you go. Enjoy.